So in last class, we have seen this probabilistic neural network. I hope you have understood that. We have taken one problem as well. So the basic concept was you will be provided training samples and they will be here. They will be residing here as weights of this network, and you will have activation functions which are like normal distribution function with center at xi and x test is your input. So that we have seen in last class. So that was implementation of Parson window. Now the next concept that is known as k nearest neighborhood estimation or k nearest neighbor estimation. This is also a non-parametric density estimation method. Now the Parson window is called as shrinking window method. As your number of samples grow, what we do, we shrink the window size. Okay. Now this KNN or K nearest neighbor estimation is called as growing window. So when your samples grow, number of training samples grow, your window size increases. Okay, so that is the basic difference. Now there is one more method in that will come in maybe next class or possibly this class called as KNN rule. That is K nearest neighbor rule, and this is K nearest neighbor estimation. These two things are separate. Okay, they are not same. The names are similar, but they are different altogether. Don't get confused in these two say words. They look very similar, so don't get confused in exam. So whenever I say KNN, simple KNN, it basically represents KNN rule. And whenever I say K nearest neighbor or KNN estimation, it represents what we are seeing currently. Okay, so KNN procedure is like this. We will center a cell about X. So this is suppose the scale, and we want to estimate probability around this sample. So we will place a cell around it, and we will see that if there are say 100 training samples with us, then square root of that is my Kn. So that is 10. So now I am in search of 10 samples in this window. Now if I place with some initial width, say some width h, and then I find that okay, there are only 5 samples in this width, then I can increase this window. Okay, I will keep on increasing this window till I get 10 samples. Okay, that's why the name is nearest neighbor, K nearest neighbor. So where K stands for 10 here. So we are in search of 10 neighbors. To accommodate 10 neighbors, whatever may be the size of window that we are going to do. Okay, that we are going to expand. Now what is probability density at this point is as usual Kn by n divided by volume. So if it is n-dimensional case, it will be a volume. If it is two-dimensional case, it will be just an area. If it is 1D, then it will be just a length. Okay, so meaning is that we will first of all fix this quantity k, that I am in search of 10 neighbors, I am in search of 5 neighbors, and then we will play with this volume. So we will try to adjust the volume such that those many k's are accommodated. Okay. Now what is the procedure in Parson window? That we don't fix this k's. Same formula, say if it is Parson, then kn by n divided by volume. So what we do, we fix volume there. We fix volume in Parson and see how many samples do fall into this volume or window. Now exactly reverse is the case in KNN, where we fix the neighbor, count of the neighbor, and then we fit a volume. Okay, so depending on situation, we grow it. So we start with a small volume and then we try to grow it so that so many samples do fall into that. So ultimately, probability density is calculated in same way. Okay, so there is no change. Only thing is how you approach the problem is a change. Now here you will find there are some eight samples here. They are spread like this. And suppose I've put k equal to 3, then you will see that the estimation is something like this. Okay, and if I increase say neighbors equal to 5, then a smoother version is appearing as your estimation. So this is p of x and these are samples. So you can see that uh, so whenever you are near these samples, you have very smooth region. The slopes are smooth, but when you go away from this, you will find that there are some distortions or jiggers in your graph. So you can see here, this is the region where you have samples, so you get a better estimation here. Okay, so like that, when you have more number of neighbors, when you are in search of more number of neighbors, then window size will increase, and you will have a smooth version of the probability density function. Okay, so these are some examples of this, and implementation is same. So kn by n divided by volume. Now there are two possibilities that can happen. If density is high near x, that is, if this is your scale, you want to find out p of x at this position, and sample density is more here, sample density is say more here around this, then you need a very small volume around this. Okay, very small volume is sufficient, and you get a very good estimation when you have more samples. Okay, when you have low sample density around x, then you need to grow this window. Uh, you have to form a big window around it, and your estimation is not that good. Okay, so higher density will give you more accurate results. But that is not in our hand, how many samples will be provided to us. So it should be remember that this is going to happen with this method. So we can obtain a family of estimates by setting say kn equal to k1 into some square root n. So instead of kn equal to root n, we can play with this k for different values by setting an extra parameter k1. So we can put some arbitrary value of k1, and then we can find out basically different kn values. Okay, so that is what this means. Now, there is a problem with this method. Suppose I have only one sample, say n is 1, then kn is square root of n is equal to 1. So we are in search of one neighbor, and the estimate becomes, say, p n x is equal to kn by n by volume. Then this n is 1. Okay, this number of samples is 1, so k is also 1, so this will be 1. And what is this? This is the volume, and this is since example of only you can say one dimension. Suppose this is your x given point, and this was your sample, training sample. Okay, so the distance between these two, I can say it is some x or x1 minus x. So what happens is you will fix actually a volume, or you need to fix a volume of this much length around x, because right hand side length and left hand side length are same. So this will be actually uh, this point will be x minus x1. So this distance is twice of that. Okay, so let me clear it. I repeat, say this is the given sample around which I want to estimate density, and this is the trailing sample x1. To accommodate this point, I need to have this size window. And what is total length is twice of this length. Okay, so this is twice of this length, and this length is, say, x1 minus x. So if I take, say, mod of this and just multiply by 2, then this will be the total length. So divide by v means it is twice 1 x by x minus x1. Now note that we don't have any control on growth of the volume. It can grow as per the requirement to accommodate those many samples. In this case, k equal to 1. So it will keep on increasing its size till it reaches to that only available training sample. Okay. So what happens due to this, since there is no restriction on growth, this PNX will be always will be giving you always some value, and it will never go to zero as such. And due to that, we will face a problem that this probability density, so integration of probability density over the x, this should be 1, so that will never happen. So you can see that this is not touching to 0 anywhere. So this will be slightly away from 0, and so this volume or this graph is never touching 0. So integration is that way infinite. Okay, but we want a finite kind of a thing. So that is the drawback of this. Okay, but anyway, if you keep this thing in mind, and then if you still use it, there is no harm in taking decision based on this. But you should keep in mind that this may be the problem here. Now you can see if I have only one sample, say n equal to 1 and k equal to 1, then this is a very crude kind of estimation that is happening. If I put n equal to 16 and k equal to 4, and I am estimating for a normal density function, then you can see this kind of graph is appearing. Now ideal graph is here. Okay, so this is a normal distribution curve that is realized when you have infinite samples and you set kn equal to infinity. So this is ideal. Okay, and this is a mixture of triangular and uniform distribution over a range. So this is possible only when you set n equal to infinity, kn equal to infinity. So which is practically not possible. So what is possible is these particular graphs with limited samples and limited number of k's. So we will take one example so that what I have said is more clear. Now let us have these many samples. This is a set of samples given to us, one dimensional, and we want to find out, say, probability at x test equal to 3.1. Now, since this is k nearest neighbor estimation, our window size can grow. Now, for the sake of simplicity, I have taken initial h to be zero point 0.5. Okay, you can take a lesser value also. So if you write a program for this, then you can set different values. So program will do this counting job, that we will do it here manually. Say k is 6, that means I am in search for 6 neighbors around 3.1. Okay, so these are some samples here. You can count how many are there. So that is my n. Okay, we find out this. Now, so the window, initial window is 3.1 minus 0.25. So what you do, you take this h and divide by 2, since total length of window is h, and you want that you will keep here. I should draw somewhere else. Suppose this is my scale. This is my x equal to 3.1, and when I say h is 0.5, that means I am searching for the range 0.25 this side and 0.25 this side, so that total is 0.5. Okay, so you keep half this side and half left side and half right hand side. So what I do is h equal to 0.5, that means half of that is 0.25. So 3.1 minus 0.25 is lower side, and 3.1 plus 0.25 is higher side. So total range for my window is 2.85 and up to 3.35. Now in this range, you start counting how many samples from this list fall. Okay, so I'm repeating that here. So this 3 here, I think 3.2, and one more 3 is here. Okay, so there are 4 samples, but I want k equal to 6. So this is not sufficient window size for me. So I need to now increase. So we will increase window size. Now let us say that I have increased from h equal to 0.5 to now h equal to 1. So I have taken a big window now. Then I am in again search for the count. So this was 3.1. Now this side I will go 3.1 minus 0.5, and this side I will go 3.1 plus 0.5. So maybe 3.6. So in that range, we will search for uh, the samples. How many samples do fall in this range? So I marked here. So this is 1, 2, 3, 4, 5, and 6. Okay, so I got 6 now. So this is by chance. Okay, you may get more, you may get less again. Then depending on, you have to take a decision. Now suppose I got this 6 and I am interested in 6. Okay, so let us say 6. Total number of samples are 20 in this list. So this list is with n equal to 20. Now volume here is 1 because my window size is 1. Okay, so estimation of P of x at 3.1 is 6 number of Ks divided by 20, that is number of samples divided by volume, so that is 0.3. Now we take another problem. Here problem is classify x test is equal to 3.1. Now you are provided now two lists. This is for omega 1 and this is for omega 2. So this is class 1 list and this is class 2 list. Okay. Now this list is with me and I am asked to do this classification based on KNN estimation. Okay. Now let us assume some k equal to 3 and h equal to 0.2. So you can try at home with different combination. Basically, you may write a program and then you can play with that. Then if I say k equal to 3, h equal to 0.1, now we have to do that estimation for two different classes. So let us take omega 1 first and take the list of omega 1. Now here I have 20 samples and h is equal to 0.2. So I will go around 3.1 minus 0.1. So this is my initial value or the lower limit and 3.1 plus 0.1. So this is 3 comma 3.2. So that range I have fixed for window initially. And then I count how many samples from omega 1 do fall in this range. Okay, so this is sample 1 in that range. This is sample 2. This is sample 3. Okay, so I have 3 samples and I was in search of k equal to 3. So that is satisfying my condition. Okay, so next step is to find out the estimation for omega 1. So now here instead of simple p of x equal to 3.1, I am writing this thing, p of probability of x equal to 3.1 given omega 1. So since I am considering only omega 1 samples here, condition is that I should have only list of omega 1 samples. So I write that as a conditional probability that p of x given omega 1. So this is likelihood actually. This is likelihood of 3.1 in omega 1. So 3 by 20, since number of elements or samples in omega 1 are 20. So 3 by 20 by 0.2, that is h. So it is 0.75. Now we will repeat or we will do the same procedure for omega 2. Now here I have h equal to 2, so I start with same value of h and I take same range, but I find in this range, say 3 and to 3.2, I have only one sample. Okay, so count is 1, which is not sufficient. So what is remedy for this? To increase the window size. Now I increase suppose to 0.4. So I again find out window limits. So these new limits are 2.9 and 3.3. Okay, so it is 0.4 divided by 2. So remember this 3.1 minus 0.2 and 3.1 plus 0.2. So whatever window is given to you, size given to you, you just divide it by 2 and then you find out limit. You will find still the count is 1. Okay, so this is not sufficient because I am in search for k equal to 3. Okay, then I increase window size further. So now it is 0.6. So I'm increasing by step of 0.2. Then I find out new limits. Now the count has gone to 2. Still not the count that I am in search for. So I increase the h further. So now my h is 0.8. So this is the limit and still my count is 0.2. So increase further. So this example I am taking intentionally to show you how this h is controlled or how it is expanded depending on my requirement. Now I have gone from zero point 0.4 to 1.0. So this is my limit. For this new window, my count has gone to 3 and I was in search of 3, so I will stop expanding my window here. Then I go forward the estimation for omega 2. So since it is taking into account only omega 2 samples, don't mix omega 1 and omega 2 samples for this purpose. Okay, so that is a caution. So whenever you calculate for omega 2, use omega 2 samples. When you calculate for omega 1, use omega 1 samples. Now here it is 3 by now 11 since count for omega 2 is 11. So this is 3 by 11 divided by volume. So it is 0.27. Now our estimation is over. Now we can use Bayes to find out probability of omega 1 given x. So use Bayes as usual, and it is 0.48 by px. So I'm not calculating px in this example. Probability of x. X is here, remember this 3.1. I think, yeah, x is 3.1. Here use Bayes for class 2 and you will get this quantity 0.095 by p of x. Now what is the final decision? X was 3.1. Probability of omega 1 given x is 0.48 by p of x. Probability omega 2 given x is 0.095 by p of x. Okay, so this is common thing, I need not calculate. Now to take decision with minimum error. Using base, we need to choose this particular term since it is higher than 0.095. So my final decision that x is equal to 3.1 belongs to omega 1. Okay, so this is my classification. So I hope you have understood this use of k nearest neighbor estimation. Now we have seen two methods which do estimate likelihood. Okay. So these are likelihoods that we have estimated either using Poisson window or using k nearest neighbor. Now these are methods which estimate likelihood, that is probability x given omega I. So this quantity was estimated, and based on that posterior was calculated. Now posterior is what? Posterior is omega I given x. This was calculated and decision like this was taken. Now, if it is possible to calculate this quantity directly, if I am able to calculate posterior directly, so this side, left hand side, if I am able to do this, I need not do all this. Okay, so I am not interested in this side, right hand side. I am interested in left hand side actually, so that I can take this decision. If somebody provides me these two things, I will not calculate these two things. Okay, I will even not estimate likelihood. Now, if that is possible, then those methods are better than these previous two methods. And that's why the next method, called as k nearest neighbor rule, k nearest neighbor rule, not estimate. So k nearest neighbor rule is very popular till date. Okay, it directly calculates the posterior, and procedure is so simple that in implementation is very easy. Okay, so that we will see. So here we will estimate this posterior directly from data. Now this k nearest neighbor rule, here the problem is classify x by assigning it the label most frequently represented among the k nearest samples and use a voting scheme. In this example, x should be assigned to one of the uh, two classes, that is red one or black. Okay, so what I mean here is, say this is a 2D case, this is my variable x1 and this is my variable x2, and this is a spread of data. So red is suppose class 1 and black is class 2. Okay, and suppose this x is given to you as x test. You want to classify this. So what this method will do, irrespective of labels, say this is my x, suppose in 1D, irrespective of labels of the training sample, it will try to find out k number of neighbors. Okay, so it will keep on expanding its volume like kind of a thing, which accommodates k samples. They may be of omega 1, they may be of omega 2. So once it is accommodating k samples, it will stop. Then it will see that out of the available k, how many samples do belong to omega 1 and how many samples belongs to omega 2. Suppose I am in search of, let us say, k equal to 7 and I got 7 samples near to this x. Out of 7, suppose 3 samples belong to omega 1 and 4 samples belong to omega 2. So majority of the samples around this x, they belong to omega 2. So my estimation is that x should be omega 2. Okay, so it is kind of a voting. So whatever is your surrounding, in that surrounding, you see how many samples belong to particular class. Suppose I take this example, x equal to this x test, and I say k is 5. Then you see that there are 5 samples around this x. So I will stop my window growing and then see that black, there are 3 samples around x, and for red there are 2 samples. So I said black is class 2 and red is class 1. So since class 2 samples around this x are more in number than red, then my decision is directly class 2. Okay. So in this way, this very simple method called as k nearest neighbor rule, which directly takes into account data around a test sample. Okay, and this is said to be estimating posterior. Now we will see this theoretical diagram and say that this is happening here. So whatever I said here is based on posterior. So this decision that we are going to take, that whatever is more number of sample in my neighborhood will decide my label is nothing but the posterior. Now place a cell of volume V around X that captures K samples. So that is the first step. So this is my X test. So keep window, initial window, and maybe we need to expand this so that K samples from the neighborhood are captured. Now Ki samples amongst K, so I have collected suppose 10 samples and out of that suppose 5 samples. So I call this as K and the subset of K as Ki. So Ki samples amongst K turned out to be labeled omega I. Then the joint probability of X and omega I is equal to, now see carefully, this is the joint probability of X and omega I. That means the X value that I am interested in and omega I is equal to Ki, that is number of samples belonging to omega I, divided by n divided by volume. So this is as usual from our previous estimation. Now the estimate for this posterior probability of omega I given x is equal to, so this is the joint probability. So this joint probability, the probability of omega I and x, this we can write using conditional probability as probability of omega I given x into probability of x. Okay, so this we can write like this. Now we are interested in this posterior, so I can take this second term and put into denominator. Okay, so the same thing is done here. So this is the outcome of this equation. Now this denominator probability of x we can write in terms of joint probability of x for different classes. So this pnx you can write like summation of j equal to 1 to c probability of omega j x. So that is total probability of occurrence of x in different classes. Okay. So we know that this is the joint probability of x and omega I, and here I want sum of all such uh, probabilities. So this probability for that is equal to actually k by n. So this will be total numbers k divided by n, and the numerator is ki, since this is there are ki numbers in total n samples. Okay. So this nn get cancels and the remaining thing is ki by k. So if I do ki by k gives me directly posterior. So meaning is that when you capture say k equal to suppose 10 samples, so this is equal to 10 samples, and out of that suppose 3 belong to omega 1, then 3 by 10, remember, so n is not relevant now, within the domain of k samples near u, that is 10, and suppose 3 are omega 1 samples, then your probability of omega 1 given x is 3 by 10. So obviously out of 10 remaining 7 belong to class 2. So your probability of omega 2 given x is 7 by 10. So if I extend this concept to many classes, suppose out of 10 samples, 3 belong to omega 1, so 5 belongs to omega 2, and 2 remaining 2 belongs to omega 3, then probability of omega 1 given x is 3 by 10. Probability of omega 2 given x is 5 by 10, and probability of omega 3 given x is 2 by 10. Now what is your decision where you will go? You will go always with maximum posterior probability. So your decision is 5 by 10, that is 5 samples. So in nutshell, what we have to do is simple way. In a raw language, we can say that if let me make some space. So if I take two-dimensional example, suppose this is x1 feature and this is x2 feature, and this is my x test. And suppose at the beginning of my problem I set k equal to say 10. Basically one should go with odd so that you can have a good kind of decision. If it is a two-class problem, there won't be any confusion that both of them are getting same number of samples. So if I put k equal to 10, then omega 1 is 5 and omega 2 is 5, then you cannot decide. So in such cases, basically we take odd number of uh, k. Now suppose this is x test. So what I do, I just move around and collect 11 samples around this X test. Okay, once those 11 are collected, we come out of this loop and check how many of samples belong to cross and how many of samples from collected 11 samples belongs to triangle or group 2. Whichever is maximum, you choose that particular label for X test. So that is the simplest way of implementation of KNN. So we will stop here for today. Tomorrow we will take basically example of this and a modified version of this along with this problem. Okay, let us stop here.